Hello everybody, welcome to the video that explains the methods that you're going to use for the mini project number 3 as part of the assessment for Our Universe. As you will have read perhaps in the PDF document, this project is about plotting what we call a Hubble diagram. It's not something that we have currently covered in the module. We will do so in weeks 11 and 12 when we come on to talk about cosmology and the evolution of the universe as a whole. What we're going to learn is that the Hubble diagram is one piece of evidence that supports the idea that the universe began with a Big Bang. So it had a definite beginning. Let me go to a page where there is a Hubble diagram already plotted on another web page. I'm just going to go to that now. Hopefully you can see this. I'll explain to you what these diagrams are very briefly, and also why it is that they tell us that the universe is expanding and therefore likely began at some point with a Big Bang. So the Hubble diagram is named after Edwin Hubble, who was the first person to plot this type of diagram in 1926, one of the most important papers ever published in all of science, demonstrating beyond all reasonable doubt that indeed the universe is expanding. It was not known up until that point that the universe was expanding, so this was a genuinely historical moment for all of humanity, I think it's fair to say. So what did Hubble actually do? Well, what he did was two things, really. He was observing distant galaxies, and when he was doing that, he was measuring the distances to those galaxies using a certain class of star called a Cepheid variable. So as the name suggests, the stars are variable, they change in their brightness. And it was known basically because of the work from a person called Henrietta Swan Leavitt, who was a woman working in astronomy at the time, who had also been working on looking at different types of stars. And she noticed there was a relationship between, let's say, the oscillation period or the pulsation period of a Cepheid variable star and how bright it is intrinsically, or what we would call the intrinsic luminosity. And the key point is, if you know the intrinsic luminosity of an astronomical object like a star, and then you measure the flux from that star, then you can use one of the equations that we've covered in the lecture course to determine what the distance to that object is. And so what Hubble was doing was looking for Cepheid variables in photographs of distant galaxies and measuring their pulsation periods and then determining their luminosities from that relationship that I just mentioned between the pulsation period and the intrinsic luminosity, and then measuring the flux of light received from those stars. He was able to determine the distance to the stars and therefore to the galaxies which are hosting those stars. So that's how he got this distance along the x-axis, measured in a unit megaparsecs, which is millions of parsecs. Hubble also was interested in understanding how the galaxies were moving relative to the Milky Way. And so he measured the Doppler shift of those galaxies. He did that by looking at the spectrum of light that we received from each galaxy, looking at the spectral lines generated primarily by stars in those galaxies, and we've discussed that in lectures. And then from looking at the spectral lines and knowing at which wavelengths those lines should appear, and then looking at the wavelengths at which those lines were actually observed, he was able to determine the speed and direction of motion of all of the galaxies in the sky that he was looking at. And what he discovered was that essentially every galaxy in the sky is moving away from us. More importantly than that, that the further a galaxy sits from the Milky Way, the faster it's moving. And that's illustrated on this diagram, which Hubble originally plotted using his data in 1926. So we have what I call recession velocity, or what they call here the radial velocity, measured in kilometers per second. So these are big numbers. 32,000 kilometers per second is a very fast speed. And here along the x-axis, we've got the distance in megaparsecs. And what you can see is a linear relationship between these quantities. That's very interesting. And for reasons I will go into in lectures, probably in week 12, This linear relationship tells us that the universe is undergoing what we call uniform expansion. That's a very important concept that we'll come to later on in the module. So this is a Hubble diagram, and your task is to plot your own version of this using data from something called the Sloan Digital Sky Survey. So that's just a little introduction to Hubble diagrams and their importance and how Hubble actually did his work back in 1926. You'll see that this diagram is being plotted using data from type 1a supernova explosions. Again, that's something I will talk about in the lecture course in a week or two's time. The key point behind this is that this is another type of object where we think we know the intrinsic luminosity of it. And therefore, by measuring the flux that we receive from a type 1a supernova explosion in a galaxy, then one can determine the distance to the galaxy. If I just scroll up on this diagram a little bit, what you can see here is a couple of nice images. On the left-hand side is an image of a galaxy before a supernova is exploded, but you can see a green arrow pointing at that part of the galaxy where a supernova will appear. And then we can see there's a new star arriving here on a certain date. And then if we look a little bit later, we see that the star's got even brighter. So we have a supernova explosion occurring in a distant galaxy. And type 1a supernovae, a special type of supernova, we know that they are like to have a certain intrinsic luminosity. So by measuring the flux from those supernovae, we can work out the distance to the galaxy in which the supernova explosion is occurring. And because they're so bright, it gives us the opportunity to measure very, very large distances. So the idea here is that you have some astronomical object. We're going to call it a standard candle. And a standard candle is just an object where you know the actual brightness of the object. And therefore, when you measure the flux, you can work out the distance. So let's go to the QM+ page where the project description is provided. Let's go to module assessments. Let's scroll down to the third mini project. And I'm going to talk about two things from now on. I'm going to do it relatively briefly. I'm going to talk about how we get the data and how we obtain values for the distance and the speed of recession of distant galaxies. And we're going to be using something called the Sloan Digital Sky Survey. There's a survey which measured the distances, or measured, let's say, the fluxes and the spectra, and therefore the redshift for more than 1 million galaxies. So there's a lot of data there. We're not going to use anything like that. You're expected to use maybe 10, 20, 30 galaxies when you generate your plot. So we certainly won't be using thousands or millions of galaxies. You're going to be using data from the Sloan Digital Sky Survey. I'll talk about that in a minute. And you're going to be plotting your data and producing a Hubble diagram of your own using a Python code that I've provided. And so the mini project is described here. Python code is obtainable here, and I'll show you how to use that also in this video. So first of all, let's just click on here, and that will take us to the mini project section here. And you'll notice there's a PDF document here which describes the project. I'm just going to open that. That's going to open on my screen. Hopefully you'll have read this by now. Please do read through this document before watching this video in its entirety. And you'll see that there is a section here, section 3, accessing the data. There's a link there to the Sloan Digital Sky Survey data. And it's data release 18 that we're going to be using. So the most recent release of data from this survey. Then click on there. And hopefully you can see on my screen now that's opened a web page with a title called Sky Server. So this is where all of the data is stored. There are a number of options available to us. We're going to just use two very simple options. I'm going to walk through with you how we're going to use the data. First of all, just to do a little exploration, let's go here to navigate. So you can see these are all links here. So we're going to go to navigate. And what it's going to do is open an image of the sky. There you go. You get a beautiful image of the sky. I'm just going to minimize this here. And we can zoom in. If you look at the top left of the image, you've got a little plus sign there. And you can see that it automatically is zooming in on the galaxy. So we've got a nice galaxy at the center of the image. Hopefully you can see that. But also I can pan by just taking my mouse and dragging the screen across, and you can see this image is just absolutely full of distant galaxies. Look how many there are in this image here. Wherever we look, there are galaxies, and a lot of the smaller dots are also galaxies. Some of them are stars, some of them are galaxies. Here's another galaxy here. This may very well be a galaxy here. Some of these are stars, some of them are galaxies, as I mentioned. If you just scroll around a little bit, you can see that there are lots and lots of galaxies. So have a little play with this and have a look at these images. They're really quite impressive. Just to kind of have a look at the sensor scale of it. And then I'm going to zoom out by, again, I'm using my mouse wheel here to do this. So you can either use the minus button here to zoom out and get a beautiful image of the sky, see how many stars and how many dots there are, many of those dots being galaxies. And there we go. Look at that. Fantastic. So it's an amazing data set. And as I mentioned, more than 1 million galaxies where we both have the fluxes of the galaxies measured and also their redshift. Or their measured through their Doppler shift. And I'll explain how that works in a minute. Now, this is not how we're actually going to access the data. We've got a much better way of doing it, which is going to streamline things for you. What you could do in principle is basically click on some of those galaxies and just try to see whether or not the repository here has their redshifts and their fluxes. But we're not going to do that. We're going to do something a little bit more streamlined, which will take us directly to where we want to go to. So I'm just going to click back here and go back to this where we started. There are various menu items here. And what we're going to go is just to visual tools. I think it's visual tools. Let me have a look. Yes, that's correct. I get a little list when I press on the plus sign on visual tools. And we're going to go to the bottom and we're going to go to image list. I'm going to click on there. That's going to bring us to a page here. Now this page, it comes with a default list of objects where you can just get little images of the galaxies. And so I'm just going to click on Get Images, just to demonstrate that to you. There you go, look at that. And that gives us a whole bunch of little, what I call postage stamp images of lots of different galaxies. And you can see there's a galaxy here, galaxy here, galaxy here. Some of them are quite small. That would indicate they're probably far away. Some of them are fairly large and fairly bright. That would indicate that they're closer to us. As you will have read in the PDF document, one of the assumptions that we're going to make in this project is that all galaxies have the same intrinsic luminosity, and that would imply that they're probably also of about the same size. So when you look at these postage stamp images, you want to choose a range of galaxies with different sizes, and therefore probably different distances as well, in order to get a good Hubble diagram. So we want to cover a wide range of both redshifts and also distances in order to get a nice Hubble diagram. So that's a piece of advice I'm going to give you, is that when you look at these postage stamp images, please try to make sure you get quite a range of different galaxies in terms of their appearances, so that you can take their data and use that data to plot the Hubble diagram. So that's just what comes by default, but that's not what we want to do. So what I'm going to do now is I've got this little menu item here called, or a little link, let's say, called Use SQL Query to Fill Coordinate List. So these images were found because basically there's a bunch of names of the objects in the catalog, their right ascensions and declinations listed in this top right-hand window here that I'm just highlighting with my mouse. This is the format that the website likes the data to be provided, and basically what it does, it goes and looks in its database for all of the objects with these names, these right ascension and these declination values. I'll just make a quick comment that the right ascension and declination values here are not given in the normal format. The right ascension in particular is given in what I would call decimal degrees. So, for example, 159.815 degrees. That's not normally what we would use for the units of our right ascension. You might remember from lectures it's hours, minutes, and seconds. But here they've just been converted into degrees. So don't worry about that in case you were thinking about why is the RA in some funny units compared to what you might be used to. So now coming back to this issue here of use SQL query to fill coordinates list. If I click on that, it's going to open a little window where I can basically get, I can run a little, it's like a little code in a sense, to obtain for me data according to various choices that I want to make. So the idea here is that the data is stored in a database, and we can select items from that database by issuing commands that the database understands. And the language that's used to generate those, let's call them database queries, is structured query language, okay, SQL, that's what SQL means. And this is written in a particular format. Now, what I've done on the QM Plus page is provide the format of the statement that you need to put in here. So I'm going to remove that existing statement there, and I'm going to go to the back to the QM Plus page. We're here back under the third mini project section here, and I've got a line of text here, which is the SQL command that you need. So I'm just going to cut and paste that, copy and paste it, sorry, into that window there. And I hope this works. And I'm going to do run and load coordinates. Okay, it's produced a whole bunch of new objects in this window at the top. So by running that command, it's generated a request for a whole bunch of new objects. Let's say a few words about the command before we move on. We're asking it to select 50 objects from the database. There's a particular part of the database where all galaxies, which have both got a spectrum measured and also where they've got a flux measured, are contained. And that little section is called spec photo. So I'm asking the website to select the first 50 objects to give me their object identification numbers, their right ascension and declination. I want to take those objects from this section of the database called spec photo, and where the object itself has a classification of being a galaxy. Then I'm also specifying that the redshift of the galaxy should be greater than the value of 0.05, and that basically that there are no warning messages associated with the quality of the redshift measurements. Okay. And so having basically run that little command, the website goes into the database and extracts the top 50 objects. So let's now get those images by just clicking Get Images here. So now you should get a nice group, 50 images. You can see now we've got a bunch more images than we had before. We've got different types of galaxies here. And here I think you can really see that there are some bigger galaxies and some smaller ones. For example, this object here, the second object that we come to in this set of postage stamps, really is quite a small little galaxy, isn't it? And it's also quite red. That tells me it's been significantly redshifted. It also tells me, because it's small, that it's far away. So that's going to be an interesting object for us to analyze, whereas there are some other objects which are clearly closer to us, like this one here. Now, the key point is that having these objects in front of you, you're going to just basically make a random selection of these objects and obtain the data for your Hubble diagram. And I'm going to explain how to do that right now. So let us go to one of these objects. Okay, let's just go for, I'm just going to randomly pick one, some nice looking galaxy. So I'm going to go to this one here. No reason in particular, looks like a nice galaxy. So it takes us back to this page that we sort of saw earlier on with sort of larger scale view. And if you look on the right hand side, you've got a bunch of links here, which you can go to. I'll say a few words about this image, okay, and about the galaxy in it. So we're given some information here on the top right. We're told its right ascension, its declination, what type of object it is. And then we've got these strange numbers here, U, G, R, I, Z. I want to make one thing absolutely clear here, super important that you understand this. The letter Z is used both for denoting redshift and also for denoting the brightness of an object when it's measured in a particular range of wavelengths that are in the infrared part of the spectrum. And those two things are absolutely not the same thing. So redshift is not the same as this Z number here. And we're going to be taking redshifts from this website. So just want to make sure that we never ever use these Z values here to represent the redshift, because that would be the wrong thing to do. So a few words about these numbers here. These are what we have covered already in lectures. They are the apparent magnitudes of the galaxy, but measured at different wavelengths. So U, probably ultraviolet. And then G is kind of green part of the spectrum, the sort of middle of the visible part of the spectrum. And then R is in the red part of the visible part of the spectrum. And in fact, that's the part of the spectrum that we're going to be using. So we're going to be taking what we call R magnitudes, or apparent magnitudes measured in the R band. We'll call this the R band. So it's a range of wavelengths in the red part of the visible part of the electromagnetic spectrum. Then I starts getting into the near infrared, and then Z is a little bit further in the infrared there. So we're not interested in these other numbers, just the R number. We're also going to be able to get the redshift, and I'm going to explain how that is done. So the first thing to do is we're going to go to this little link here beneath this little zoom in image. This is an image of the galaxy, which we've got here. I'm going to click on that. And it's going to open a page. And it's going to give us all of the data that we need. And let me show you how that is, or where the data is. First of all, it's going to give us the apparent magnitude in the red filter. And for this particular galaxy, the apparent magnitude is 16.71. So we're going to use that number. Explain how we're going to use that in a minute, but let's just move on to the next piece of data. And then redshift is given in this little box here. And you can see that this redshift is 0.0512595. Okay, so that's a number that we need as well. So we need this number here, the magnitude in the red filter, and this number here, the redshift. Now, how is this redshift obtained? I'm going to explain that to you now, but I'm going to use a different example to demonstrate this to you. So what I'm going to do is just press the back button. I'm going to press the back button again. I'm going to go back to our nice set of images here. And I'm going to click on this object, which I am guessing, it is a guess, could very well be a small galaxy, which just happens to be obscured by dust and therefore gets quite red, but I suspect it isn't. So I'm going to click on this image here. That's going to take me back to this page here. And then I'm going to go back to quick look. So here's our galaxy. Here's our quick look. So what can we see from this galaxy? Well, first of all, it's got a apparent magnitude in the R band now of 19.49. The previous galaxy had a value of about 16. Now, remember from lectures that having a larger magnitude corresponds to a dimmer object. So this is dimmer, and it's got a larger magnitude. So it's what we expect it to be. So there's 19.49. So there's our magnitude. And look at this. Our previous galaxy had a redshift of about 0.05, and this one is 0.48, so almost 0.5, so almost 10 times bigger than the previous one. Where are these redshifts coming from? Well, what we've got on this page is the opportunity to have a look at the spectrum of the galaxy, and that's what we use to derive the redshift. So I'm going to click on this spectrum, and it's going to show us these different lines, okay? And the interesting thing here is we can see that different lines or different parts of the spectrum are indicated by basically some labels which correspond to the spectral lines which are associated with different chemical elements and different spectral lines generated by those elements. The ones shown in red are generally what we call absorption spectrum lines, or so this is part of an absorption spectrum. But galaxies can also have components of their spectra being emission spectrum, so those are shown by the blue points here. Now, the key point is that we know in the laboratory which wavelengths these spectral lines should occur. So I'm just going to, for example, take one of these spectral lines. Let me take this one here. It's the sodium D line, okay? Now I've got another window on my computer here, which I'm going to give you access to with a link. What it shows you is the wavelengths associated with different species when they're absorption lines or emission lines are measured in the laboratory. I'm going to scroll down. It's got emission lines and absorption lines. And I'm just going to note that the sodium line is listed here. And in the laboratory, we can see that the sodium line has a wavelength of 5895. What units are being used? Unfortunately, it's something called an angstrom. An angstrom is very close to a nanometer. It's just off by a factor of 10. So let's not worry about what that particular unit is. I can explain it to you if you want me to, but I don't think it's particularly important. It's just a unit of length, which is used by astronomers. So again, something else to learn about. But here, let's just look at the value that is actually present in the image of the spectrum from this high redshift galaxy. Now look at where this line is occurring. This is the line here. I'm using my mouse to kind of illustrate it on the screen. And let's just make a rough estimate of what wavelength that is. So again, it's measured in angstroms. So here we go. So that's 8,000. 100, 200, 300, 400, 500, 600, 700, 800. So I'm going to make a rough estimate. It's 8,800. Now, if I can measure the wavelength of the spectral line in the spectrum as I observe it in the galaxy, then I can, and I know what it's meant to be in the lab, then I can work out the redshift. And so what's that going to be? I'm going to just calculate it now. So it's 8,800 on my calculator, minus the wavelength in the lab. So that's 5895. And then I divide that by 5895. And that gives me the redshift. And look, that's very close to the value that I just quoted a few minutes ago. Let me show you that. Here's the redshift that I quoted, 0.48. And I'm getting a value of 0.49 because I didn't quite measure the wavelength of the spectral line perfectly, but I got it pretty close. So that's where it comes from. That's where the redshifts come from. So by analyzing the spectrum and looking at where the spectral lines are appearing in the galaxy spectrum and comparing those with where they would appear in the laboratory, we can work out the Doppler shift of this galaxy. And remember, that number represents the velocity of the galaxy relative to the speed of light. So this object is so far away and it's moving so fast, it's actually moving at almost half the speed of light. That's what it's telling us. So that's kind of an interesting little thing to mention. So this is a fairly high redshift galaxy. Okay. Now it turns out, I won't go into this in any detail, redshifts can be bigger than 1. Objects can be expanding away from us as part of the expansion of the universe at faster than the speed of light. Reasons for that are complicated, but it's to do with the fact that what's really happening with the expansion of the universe is space itself is stretching outwards at a high speed. It's not, so this very large redshifts, or the large redshifts you can see, which exceed 1, don't imply that the galaxies are moving through space at faster than the speed of light, but only that space-time itself is stretching at very high speed. So there's a subtle difference there, which is very important. Anyhow, let's go back to this galaxy then. So we have this galaxy here, we have the redshift, and we have the magnitude in the R band. What are we going to do with this? Well, what you're going to do with it is going to put this data into what I'm going to call now a Jupyter notebook. Hopefully you know what one of those is. It's basically a piece of Python code which is going to allow you to put the data into it, and then it will generate some plots for you. And I've very kindly produced that for you, so you don't have to write that yourself. So how do we get the Python code? Well, I'm going back to the mini project part of the QM Plus page. I'm going to just go back a little bit. I'm going to go back to the projects themselves, and then you will see here that I've got the Python code sitting here. So I'm just going to click on this. I'm going to get it to download. I'm going to download a linked file as, that's how it works on my computer. And I'm going to ask it to basically go here. I'm going to create a new folder, and that folder is going to be called Project 3 Demo. Let's call it that. Okay, I'm going to create that. Let me call it Our Universe Project 3 Demo. Our Universe Project 3 Demo. It's going to create that file, and then hopefully don't like the way it's doing that actually. It's doing something quite strange. I'm just going to cancel that for a second. We'll click on there. Ah, there you go. It seems happier now. Yes, it's gone into my downloads folder. That's better. What I'm going to do now is open up and go to my downloads folder. I'm going to copy that. I'm going to go back to my home directory, and I'm going to go to that folder that I just generated called Our Universe Project 3 Demo. And you will see I now have a file there. It's probably a bit small for you to see on the screen, but the code is called Hubble Diagram Python Code. And there's IPYNB on the end, which means IPython Notebook. And this is because we're going to open the this code using some special software. Okay, so let's do that. How do we open the software? Well, I'm going to be using something called Anaconda, which is a particular installation of Python. I highly recommend that you install that on your own personal computer. It's going to be very useful for you to use throughout your degree program if you haven't done so already. I know it as part of your professional skills for scientists, you've been learning about some Python coding. You may very well have been using something called CoCalc. That's something else you could also use. So you could upload this code into CoCalc and use it there. You may also be familiar with some free online versions of Python. In particular, Google has something called Google Colab, where you could also upload this code and use it there as well. So we don't need any data to download. We're going to be just inputting the data by hand into the Python code and using it to plot. So let me get my Anaconda Python working. So I'm going to go here. So this will look different on your computers. You're probably using Windows machines. I'm using a Macintosh. So things always look a bit different. I apologize for that. But I'm going to open Jupyter. And here I just opened Anaconda. It gives me options to open different types of programming environments and different types of code. I'm going to generate what we call a Jupyter notebook. So click on launch, and it's going to launch for me a web page, which will give me access. So here we go. Great. So this is what happens on my computer when it opens. You basically get a whole bunch of different folders that you can access and files. And I'm going to go to Our Universe. Where was it? Our Universe Project 3 Demo. Yeah, I'm going to click on there. Double click. And that then opens for me the folder. And you can see that I've got the Hubble diagram Python code sitting there. So I'm going to click on that. In fact, I'm going to double click on it so that it opens and runs. So I double click on there. So that's where I saved it. And then here it is. Now, a quick word of warning. This has already been run in the past. I need to make sure that basically I restart the kernel and clear all output. So I'm going to do that. Okay. So that means that all of the stuff that was produced when I ran the code before has now been cleared out. And instead, we just have a clean Jupyter notebook, which when I execute it will generate some output. A few words of description here. You may know this already, but these Jupyter notebooks have two types of cells. One of them is what we call a code cell. So here would be an example of a code cell I'm clicking on right now. And we have something called markdown cells where you can write nice looking text. And this would be an example of a markdown cell. I'm going to double click on that. For all types of cells, in order to execute them, what I do is I do a shift and I do an enter. And you see when I do that, it converts that slightly weird looking stuff that I had before into some nice looking text. So please work through this Jupyter notebook and look at it. Make sure you understand what's going on. But I'm going to just slowly scroll through now and explain what it's doing. And then I'm going to demonstrate how it actually works. So first of all, what we've got to do is import some libraries. into our Jupyter Notebook for plotting, for doing mathematical manipulation, for generating what are called arrays, and for using some special functions that we use to actually fit a line to our data. Next, we actually have a little code cell, which is the where you're actually going to put your data. And what I've done is I've already read off from 4 random galaxies from the Sloan Digital Sky Survey the magnitudes in the R band and the corresponding redshift. So you'll see here that I've got basically an array. I've called the array RMag for the magnitude in the R band. And I've got a number of values there, 16.82, 17.61, 17.39, and 16.09. As I go through those postage stamps, they're not in order. So as I went through them, I just basically put in the R magnitude values, or the magnitudes in the R band that I came across when I looked at the random different galaxies. I also then put into this array the 4 values that correspond to the redshift. So for the galaxy with 16.82, it has a redshift of 0.1202, blah, blah, blah here. I've got another galaxy here with a magnitude of 17.39. And it has a slightly bigger redshift of 0.1235886. So look at that. So each one of these magnitude values has a corresponding redshift, and they must be in the same order. So 16.82 must correspond to this one here, 0.12. So as you go through the data, what you're going to do is the following. So let's do a quick example. I'm going to go back to the image. So it's a quick look. This is the one I was looking at. Remember this little red galaxy here? I'm literally going to just cut and paste this number, 19.49. That's my magnitude in the R band. And I'm going to come to my Jupyter Notebook, wherever that is, here. And I'm going to put it at the end of this list of galaxies. So that's my magnitude. I'm literally going to paste it in. There you go, 19.49. That's my new R band. And then I'm going to go back to that page that we had before. I'm going to cut and paste the redshift. So I'm going to copy and paste, sorry, not cut and paste, copy and paste. And then I'm going to put that on the end here. And there we go. So I've got a redshift and a magnitude that correspond to each other. I've just added those to my data. So how is that going to look? So now I'm going to execute the notebook line by line. So first I'm going to come to this code cell. I'm going to execute it. That's going to load my libraries. Now I'm going to come to this code cell. I'm going to execute it. And that's going to define my arrays and put the values into them. So I'm going to have an RMag array, and I'm going to have a Z shift. Z shift corresponds to redshift, and RMag corresponds to the magnitude in the R band. I'm going to click on that. Then I'm going to come down to this next I'm going to call it code cell. I'm going to execute it. I'm going to show you what it does first before we talk about it. And you'll see it generates a plot for us. And the plot that it's generating is redshift versus R magnitude. Redshift on the left side, R magnitude on the x-axis here. See the R magnitude scale between 16 and 19.5. You can see the redshifts now go between 0.1 and 0.5. So that's our last galaxy that we just put in right up here. You'll also notice that there is a best fit line has been drawn on this. That's been generated by a Python function, or a method as it's sometimes called polyfit, okay? And it basically fits a line to data. So that's where that's come from. Now, the Hubble diagram itself is not plotted as redshift versus magnitude. Instead, what it's plotted as is velocity against distance. So we need to do some work to convert these numbers into the appropriate values. So redshift is easy. If I have the redshift and I multiply by the speed of light, then that gives me the velocity. And so long as I have the speed of light in units of kilometers per second, I'm going to get velocities in kilometers per second, which is what I want. The conversion of the R magnitude into a distance is a little bit more complicated, and it is explained in the PDF document. but let me just go through it again very quickly. So first of all, we've got a magnitude, and you'll remember that the magnitude scale, this is something that we covered in lectures very recently, is related to the flux that we receive from an object. So it can be a star or it can be a galaxy, and in this case it's galaxies. And you may also remember that we use the star Vega to calibrate the magnitude scale. So what we're going to be doing is using the flux that we get from Vega. We're going to be using the equations that we introduced in lectures, but also which are presented in the PDF document, to convert our magnitude into a flux. And that's done with a little equation here, which I'm showing you in this cell that describes what we're doing. But the actual line that does that in the code is given here. Okay. And then once I've got my flux, I'm going to use my relationship between luminosity, flux, and distance to calculate the distance. And instead of using Cepheid variables or type 1 supernovae to measure the distance, what I'm going to do instead is assume that every galaxy has the same intrinsic luminosity. And I'm going to assume that that luminosity is the same as the Andromeda galaxy, which is something which can be measured because Andromeda is fairly close. And it has a particular value, and I can tell you now that the value that we have there is basically 2.5 times 10 to the power of 10 times the solar luminosity. Where does that come from? Well, basically, there's around about 10 to the 11 stars in the galaxies that we see. Okay, most of those stars are somewhat lower in mass and lower in luminosity than the sun, so we get a value which is close to 10 to the 11, but not quite as big. So we get 2.5 times 10 to the 10 solar luminosities. That's where that comes from. So if I've got the luminosity, I've got the flux, which I've measured through my R-band magnitude, then I can basically rearrange this equation, an equation that we've covered in lectures, to give me the distance to the galaxy. So it's given by this expression here. And that expression there is implemented in the Python code down here. So I'm going to now execute this cell. It's given me an error for some reason. I need to find out why that is. So I execute this cell, and then it's complaining about something. Right, sorry. Why is it doing that? I did things in the wrong order. That's why. Okay, it complained because I've made a little mistake in my Jupyter notebook, but I've just fixed that now. So now I have a set of arrays. One is called distance. The other one is called Z-shift, which gives me the distance and the redshift. I've then converted my redshift into a velocity. I just need to slightly adjust this actually, because I can see there's going to be a slight problem. So I'm going to create a new array here. This is the trouble when you don't test things properly before you start recording your videos, which I'm a little bit annoyed at myself for doing, but okay, we all make mistakes. Okay, so I now need to generate for myself a new array called velocity2. I'll explain why that is in a minute. So in addition to having the galaxies that we've got on SDDS, I also want to put our Milky Way on this diagram. And the Milky Way, of course, is not receding from itself, okay? So and it doesn't have a distance from itself. The distance is 0, and the redshift and the velocities are 0. So I do want to put that into my data set as well. So I'm just appending those values of zeros into my data, which I'm going to plot. And as a consequence of that, I've basically generated a couple of arrays. One's called distance2, and one's called velocity2, which contain my velocities and my distances, but also including the Milky Way. And so now I'm going to go here, and I'm going to go here, just make sure I amend what I've got here and show you how this looks. So now I'm going to plot velocity versus distance. Velocity in kilometers per second, and distance, I've converted that into megaparsecs. And there we go. There's our Hubble diagram. It's quite nice, isn't it? You can see some scatter around the actual trend line, which has been fitted here, again using polyfit, but actually it's not bad. It's a pretty good fit to the data. And when you add more and more data, which is what you're going to do, then this will get to be a better and better fit. Now, the problem with using polyfit as a means of getting the best fit trend line is that it doesn't actually go through the center, through the origin. You see our galaxy here is plotted with this little blue point at 0, 0, that's the Milky Way, but the red line doesn't go through it, and that's not what we want. So I've got another way of doing that, which is presented in the worksheet down here, sorry, in the cell down at the bottom. And this also plots out for us the value of the Hubble constant that we need for our project. And the value of the Hubble constant, which has been measured using the most recent data from a Hubble Space Telescope, comes out to be about 73 kilometers per second per megaparsec. The Hubble constant is obtained by taking or measuring the slope of this line. Okay, and so what the next cell does is it fits a line, forces it to go through the center, and also measures its gradient. Let's try that. And there we go. We've got the red line going through the point at the center where the Milky Way is. We've got the line, as you can see, doing a reasonable job of fitting these various points. And most importantly of all, I've got the Hubble constant here. Now, I said that the Hubble constant measured by HST was 73 kilometers per second per megaparsec, where it's been obtained using Cepheid variables type 1a supernovae. Here we've just made an assumption that the galaxy has a fixed luminosity, and yet we've got a really good value for the Hubble constant out of this data, 72 kilometers per second per megaparsec. If you add more and more data, I would expect this value to get better. So that's basically what you've got to do. And now you can basically save this image in the Jupyter Notebook by right-clicking, save image as, download it, and you can incorporate that into your project. So that basically covers everything. Let me just very quickly go back through a couple of things. Just want to get rid of this floating controls, getting in the way. Let us go back to here, remind ourselves what we did. Okay, I'm just going to see if I can get this to work. Right, go here. So here we are. We can go back. Now, I'm not quite sure why I haven't got my images here. You see it's disappeared. Right, that's just not quite right. Okay. My images have disappeared. There we go, they've come back again. It must time out or something like that. I was a bit surprised by that. Okay, so here's my images. And your job is to choose, let's say, for the sake of argument, 20 galaxies at random. Now, final word of advice. Look at this galaxy here. I'm going to go for this one. And let's zoom in on it. Okay, so I'm going to zoom and zoom and zoom. Look at this galaxy. It's clearly an interacting galaxy. You've got a big tail of stuff coming off it. That looks like two galaxies which are actually in the process of colliding. I can see we've got a little bulge here, and also it's brighter here. So there are two brighter points in here, which were the central bulges of the two galaxies before they merged. I would recommend trying to avoid these types of galaxies when you're calculating, in particular, or taking the magnitudes, because these are not representative of most galaxies, and you may find that they don't give appropriate values for the magnitude. So you won't be a very helpful thing for getting a nice, clean Hubble diagram. So try to avoid those types of galaxies. Look for irregular looking galaxies. And here's an example of a regular looking galaxy. So just click in, let's just go in there. Here you can see in this little postage stamp image there on the right hand side, it's quite regular looking. Okay, let's have another look at another one. Here's another one. So again, we look here, we'll zoom in a little bit more. So there you go, nice, beautiful looking regular galaxy. probably just like the Milky Way or the Andromeda Galaxy, so behaving very nicely. So these are good galaxies to go for. Also, smaller galaxies to give you proper redshift. So again, coming down to the bottom of the page here, let's look at this image here. Okay, so again, another small red galaxy. You can see in the postage stamp on the right-hand side. I'm sure if I click on the quick look, which is what you need to do, remember, to get the redshift and that. Yeah, so look, this is a nice high redshift galaxy as well, 0.457. So that helps you fill out the Hubble diagram with lots and lots of different galaxies with different characteristics in terms of their magnitudes and their redshifts. And that hopefully then when you come to generate your Hubble diagram will give you a whole bunch of points all the way along here, which will give you then an opportunity to fit a nice line to it and hopefully get a slightly better value of the Hubble constant. But I think it's amazing, isn't it, that even just making the assumption that all galaxies have the same luminosities gives rise to a Hubble diagram, which matches to a very high degree of accuracy, one that you could obtain by taking Hubble Space Telescope data using a more accurate way of measuring distances, using Cepheid variables and type 1a supernovae. So that's enough for me. That was a bit longer than I wanted to be, but I just want to give you a full picture of what you need to do. Please read the PDF document to get information about what goes into your report. I've basically shown you exactly what to do there, so please just go through it. I hope you enjoy this activity. You know, as I said, Hubble diagram is one of the most profoundly important scientific results in all of history. And here you are, you've got the opportunity to use real data to construct your own Hubble diagram and demonstrating without any doubt whatsoever that the universe is undergoing expansion, indicating that we did indeed start with some initial beginning to the universe that we call the Big Bang. Please come and ask me for help if you need help. Ask the TAs in the exercise classes. We'll have plenty of time to discuss this project and the other projects before the end of the semester. And a final note, just to say that there is no checkpoint for this project. It's just a question of uploading it by the end of the 19th of April. Okay, so please do that. That's week 13, giving you some extra time to try to get this all done, because I know that you're all under quite a lot of pressure with other coursework, and obviously we want to make sure that we bring this to an end before you start your revision for your other modules. Okay, thank you.